Hello everybody, so I hope all of you enjoyed the lunch and you're not too tired now. So today we are talking about what is necessary and how to tune a system for super low latency communication. Maybe we start with a basic introduction of ourselves. So I'm Felix, that's Henning. We are both located, or we work where this red cross is here in Munich, which is Munich Perlach. And we are both part of the Linux Expert Center at Siemens, and there we mostly work really with the lower levels of the I would say, stack. So we do real-time Linux tuning, embedded Linux, KVM, so running virtual machines, or at least setting up the infrastructure to run it. User space I/O. We are a research department, so we don't have any products, but instead we do pre-development, create proof of concepts, sometimes also fixing bugs in products, and yeah, basically that's what we do. Maybe some of you will go to Munich anyway next week because there will be the Oktoberfest, which would take place probably there on the Theresienwiese. And with that, I would like to hand over to Henning to start the talk.
Yeah, thank you, Felix, for the introduction. Yeah, let's jump right in. What's our motivation here? What are we dealing with, and how did we get in touch with DPDK? Siemens is, as you might know, building products that are used for industrial control or healthcare or transportation, and those systems are real-time critical, which means the latency counts a lot, and usually the worst time latency is what we care most about. So average should be good, but worst case should definitely be bound. Other systems that have similar properties are like communication systems, media streaming, we saw a talk earlier, switching, of course, and real-time or high-frequency trading systems like stock trading, goods trading, what have you. So these real-time control systems, they have to compute fast or reliably, but they generally control processes in the real world, so they will have to communicate fast as well, to control whichever process they control. And yeah, as we see functions co-located on machines, we just have to assume that the number of real-time capable functions will eventually or will exceed the number of network interface cards we have, so we cannot say we'll put every single real-time function on one network interface card. Functions could be, you know, native applications, containers, VMs, what have you. You know all that stuff. So, yeah, a few words to the system setup and the implementation. When we're using DPDK or when we talk about real-time, in this setup we're talking about Linux preempt.t. Installed on a host, so you basically install that kernel. Installing that kernel makes your system real-time capable, but not behave in a real-time manner necessarily. So what you do next is you apply tuning, which basically means you isolate CPUs, you maybe change the ways the clock works, you maybe disable hyperthreads, and so on and so forth. I'm not going to go too much into detail. All you need to know is that we nowadays use a component called TuneD, which is open source, which helps you to deal with these kind of things and turn a real-time capable system into a system that behaves in a real-time manner. So now we have a real-time capable compute infrastructure and put our network functions on top. How do we get the function connected to the network, especially as we keep virtualizing? I put here 4 different ways of doing that. From the top to the bottom, the hardware cost or the cost increases. and so does the flexibility, and we'll go a little bit into detail comparing those. And yeah, you probably want to be on the more complex and flexible side because, as I said, systems getting bigger, more functions on the devices being co-located, functions disappearing, reappearing, whatever. So it's dynamic, big, and yeah. Then you know, something like a pass-through device maybe doesn't cut it. And the performance greatly differs. So that's also what we're here for, to maybe say a few words on how to measure such things. Okay, yeah, let's start off with the easy one. You have an application, you run it native, or you run it in a container, or maybe in a VM. So you basically give it a full NIC, or maybe a virtual function. Hardware-wise, that's super cheap. Software complexity-wise, that's also super cheap. It's commodity, you simply have it. Like even in smaller industrial PCs, you would have, you know, an I/O MMU as commodity, or maybe a network interface card that even already supports virtual functions. But yeah, the problems are that doesn't scale because you can't scale the number of functions above the number of NICs or the virtual functions you might have. There might not be real switching, so if you have multiple players on the same node wanting to talk to each other, you then have to rely on external switches to reconnect them. Even if you use virtual functions, you know, communicating one virtual function with the other doesn't necessarily always work, might still require an external switch. And yeah, once you maybe think about bigger systems like a HCI cluster, where you might want to migrate workloads, then, you know, having them bound to hardware is kind of nasty. It makes them harder to migrate. So, no, I skipped a slide. So here's an example of how a measurement would look like if you would say, like, okay, how much does it cost me to send a packet back and forth? And so how much latency would there be in the worst case? And in the, so what the measurement does here, we have a relatively small machine, a 4-core i5, which has 2 network adapters with a cable loop and 2 ping-pong applications that basically bounce a packet back and forth and measure how long the packet was on its way. So that's depicted in the upper right. In the lower right, we see a histogram of the distribution of these latencies. The unit there is microseconds. And in the lower left, you see the output of the application, a DPDK application, where we are most interested in the maximum round trip, the one that starts with a red max. The other stuff is statistics and average and what have you. So yeah, how do we actually measure this, and what is this L2 reflect? It's, as I said, an application that bounces a packet back and forth like in a ping-pong manner with 2 players. It supports obviously preempt RT, setting scheduling parameters and priorities, and we basically measure in each of the 2 players how long the packet is on its way. We send it out with a TX burst, and then one of the RX bursts will contain that packet and we'll say, okay, that's how long it was on its way. And we do this with polling, but yeah, we also put in interrupt support at some time. And then what you can say is that roughly, or half of the maximum you saw is roughly how long a package probably spent in one player to receive it, handle it, which in our case is just swapping the max around and firing it back, and getting rid of it again. So so what basically it gives you is what is the baseline worst case latency of a networking application in user space that is in fact a really stupid application. But you know, if you had a more advanced application, that would still be your baseline. you would have to consider. You probably won't get much faster than that. Also, we did it with DPDK, not necessarily saying that your industrial control application would be using DPDK, but we just chose DPDK because it's available, you have all the drivers, and we assume that that's best in class. Even if you write your own drivers and do this all on your own, you will probably not get better than the baseline we could measure with DPDK. So yeah, then it supports min, max, average. You saw it on the previous slide. Some histograms, some statistics, what have you. And it inspired by an application called cyclic test, which is a way of measuring the baseline compute side of real-time Linux. It leaves markers in the kernel tracer and has a feature where you can stop a measurement when a certain threshold, when a spike in latency overshoots a certain threshold, so that the trace ring buffers are stopped, and you can read the trace. Your events, caused your spike, are not overwritten, and you can find them in your trace. So yeah, again, what is it? Simple, super simple micro benchmark, nothing more. But it also turned out that it's a pretty universal and quick way to measure any real-time or any network for its real-time capabilities. So you can, take two PCs, put a cable in between, and measure that, and then say, okay, that's what those two processors and what the NICs need. And then you add maybe a couple of switches or other delay elements, and you can see what those delay elements add. And so that's a tool to quickly judge a network on how fast, or how fast, in the worst case, it can transport your packets. And interestingly, for us, most interesting, like you can judge a virtual network. So like, you take your application, you take it from native into a container. Does that change anything? You take it into a VM, which virtualization mechanism is the fastest? And you can answer these questions pretty easily. And it helps you find tuning problems, and it helps you quickly detect if you, for example, if you lift the reflection app into a QEMU with E1000 emulation and run the whole thing over a Linux bridge, you'll see that that's not the best idea, pretty quickly. And of course, you can use it to continuously monitor your software stack if, what was once good is still good. So yeah, we already sent it to the DPDK mailing list 2 years ago. Hope to get it upstream. Last week, Felix sent another round. We'll keep trying. Otherwise, maybe we'll put it on GitLab, on GitHub somewhere. We think it's a useful tool. We've used it to compare our own setups with OpenStack. We are partnering with VMware and with Red Hat to evaluate their setups. And it's always a great tool to say, like, okay, that's the real-time capability of the CPUs you give us, and that's the real-time capabilities of the networks on the network virtualization you can provide. So here's a few examples. I wanted to have a demo, but yeah, we'll stick with screenshots. That's a pretty well-tuned Xeon system where the maximum would be 31 microseconds. So we are talking 15.5 microseconds for one CPU and one NIC to receive a packet and send it back. And then we introduce a few mistakes. For example, we schedule one of the players on a best effort core where there is additional CPU load. You quickly get 4 milliseconds, so like, order of magnitude worse. The average is still good, but as I said, we don't care about the average. And here's another one, 2 TAP devices over a Linux kernel bridge. Also not ideal, I would say. But yeah, so going back to the actual point away from our measurement application is like, so how do we, what could we measure next? So we can measure how much it costs us to to use different connection methods to a virtual network. And then next thing was like, okay, but that's not going to be useful because it's not going to be a real switch. It's not going to have the dynamics we need. And so we said, before we try such a real switch, and that was actually several years ago when there was none available, we said like, okay, we can at least measure how much it would cost us if there was a switch that every packet had to pass through. So what we did is a simple adapter, one physical NIC to one vhost user, and we hooked that between the virtual machines, or maybe just one, and having the other player sitting native. And yeah, using polling mode, super wasteful, like waste the whole CPU on pumping the packets back and forth. And yeah, then used our measurement application to see how expensive that would be, again, in the worst case, just looking at the latency. And yeah, this application has similar threshold and tracing mechanisms, but I'm not going to go into detail. We also did not propose this one for open source. Later, we extended it a bit to put it more into efficient use by using VMDQs, so experiment a bit with offloading, but we quickly stopped this and said, okay, the numbers are good. It's promising. It's for many of the use cases, it's probably a good idea to have a software switch, but we'll stop here and rather look at an existing one. Now that we know that the latencies of a well-implemented software switch are probably acceptable to most of our applications. And with this, I hand over to Felix.
Okay, so the next step was to actually test how well the Open vSwitch is suited for this kind of real-time communication. Because as Henning already mentioned, we have a couple of VMs, and we want them to be able to communicate with each other as well as communicate with the outside. And probably the solution that comes into mind first is using the Open vSwitch for that task, because it's exactly made for that. And before we actually do that or integrate it into a product, we really want to measure a baseline, how fast we can get with the Open vSwitch, and if it's real-time capable, if it's suited for this scenario. So what is important for this kind of benchmarks? It has to be fully reproducible. Otherwise, you do it once and you cannot reproduce it. It doesn't really have a value. So what we did is we built an Debian 11-based bootable image. We assembled that with the ISA build system that's open source as well. But that's not the point here. We used a relatively modern kernel with the preempt RT patch. We used Open vSwitch 2.15, both without any modifications as well as with a modification we need for the Profinet protocol to be able to match on quality of service fields in the Profinet protocol. We also bootstrapped the configuration so that you just boot up the system and don't have to configure anything. And then we hooked up two Intel i350 cards, so in total we got 8 physical ports. And we just put all of these ports onto a single DPDK bridge with standard forwarding, which is just the Mac learning flow. If you look at the picture here, it looks like this one, where on the left side you see the test system. That's the system we really want to evaluate, where we run the Open vSwitch on. On the right, you see some kind of system which we use to measure how real-time capable the switch is. By just inserting packets from the right side to the left side, then they get handled as with a hardware switch, or similar to a hardware switch, and get somehow sent back. And then we can see here how long did it take, did the packets got handled correctly, and so on and so forth. And the switch test system here can be replaced. So let's have a look at the infrastructure. One thing that is really crucial when you do real-time tuning is to know your system and also to monitor and measure if the system is always real-time tuned, because there are some events that happen while running the system that break the real-time. One example would be an interrupt showing up on a real-time CPU. And in the end, when you're done with your measurement and you see a latency spike, what do you do with this information if you don't have any monitoring? But if you have the monitoring, then you can correlate that by the time that spike happened and see what happened on the system itself. So how does this look like? I mean, here in blue we have the Open vSwitch, which is pretty standard with the DPDK bridge and the NICs. Then we have our TuneD, which we use for tuning the system for real time. Of course, we need some additional tuning on the kernel command line, which cannot be done at runtime, like specifying the ISOL CPUs, specifying which kernels should be run in tickless mode, specifying IRQ affinities, disabling all the power saving things, because power saving adds a lot of noise to the measurements, especially if you do not run the system under a high load. And then we add a telegraph-based monitoring infrastructure. By telegraph, because telegraph has a plugin infrastructure, it's easy to extend the tool to have to write custom plugins to get some additional information. And it's an open source tool, and you can simply collect data and then send that over to an InfluxDB, which is then hooked up to a Grafana dashboard, so that you easily can see in a Grafana dashboard how well your system is real-time tuned. We also wrote a custom plugin for the OVS, which gets us some basic information like the utilization of the poll mode threads. So these are basically counters how much time is spent while moving packets around and how much time is the thread spends for idling. We also reset these counters each second so that we really get the values over time and not just in a run to completion manner. And also get some other things like packet statistics. But that's basically it. So from the OS side, we're interested in mostly in the interrupt queues or in the interrupts that happen, also in the non-maskable interrupts per CPU. And from OVS side, we're interested in packets and the cycle time. And then we did a very basic measurement with this layer 2 reflect application. So what we did there is to set up the OVS system as discussed there and hooked another system next to it connected via an Ethernet cable. There we started 2 instances of the layer 2 reflect application, and the expectation is that the packages simply are sent to the Open vSwitch, then they are handled here, reflected back. We see them show up here in the second instance of the application. Then they are reflected. And once they are back here, we can measure the time and see how much this whole round trip over the Open vSwitch over 4 NICs took. No, I don't see the slides anymore. OK. The good thing about this measurement is that it's very simple. And by that, you get some idea what numbers can be achieved. And it also has some nice properties, like it's much easier to find latency spikes with these simple benchmarks, because there you can easily do the tracing things Henning was talking about, than with a full-blown switch test measurement. And we did that, and we found some issues. At some point, we also patched the OVS to log packets with our magic payload, because then we were able to really get traces from when did the packet enter here, leave here, when did it enter here, which parts of the OVS are traversed, things like that. And also we were able to break if the latency was high and then have an in-depth look at the OVS to find the root cause of the test. Finally, we also put some stress on the Open vSwitch on the non-RT cores, so just CPU, memory, TLB, cache stress with the stress NG tool to have more realistic settings and not just whether measure the good case. And if you look at the results here, we got latency, I mean, we run it for like 20 minutes. We got some pretty good latency numbers for this whole round trip going back and forth, which took 130 microseconds. And it also shows that we are pretty close to how well we could get, because if you compare the maximum and the average, you see that there's not too much difference in between. So that is an indication that we have done the tuning well. But 20 minutes is not enough. So when running the same test for like 10 days, you get some different numbers. Here we have like 184 microseconds, but this is still in the range we expected, and in our opinion, it shows that the system is well tuned. But the point I want to make here is that if you do this kind of stochastic measurements where you just observe, but you cannot really prove that the system is real-time capable, you never can prove that, you really have to run these measurements for days, and your application have to support that. That's often not the case if you use switch test systems. And assuming that the process priorities of both of the OpenV switch as well as of the measurement applications are correct, these latencies likely come from interrupts. But to see that, or to confirm that your assumption is correct, you have to look into these interrupt counters to see if that could be a root cause or not. Okay, moving on. The next, after we got these measurements, we were quite happy, and we said, okay, now we need a more realistic scenario, because with these L2 reflect measurements, we don't put much traffic on the OVS, so it's not really realistic. Also, we measure both real-time systems, or both operating systems, one of the OVS and the one of the test system, at the same time. But we tune both of them. So we don't know, did we make the tuning issue or the tuning error in the measurement application, or really in the OVS system? And then we could just measure 2 ports, and we had a very simple communication pattern, which is easy for the OVS to handle. So instead of continuing with that, we moved on. Luckily, we have a Spirent hardware switch benchmark system. There we can be pretty sure that there are no real-time tuning issues in the system itself, because it's made for measuring hardware switches. The system can run standardized benchmarks like the RFC 2544 benchmark, which is a pretty commonly used switch test benchmark. And you also can test all ports in parallel. And then you can play around with the frame sizes and see how the load and the latencies change if you change the frame sizes or the amount of packets you insert into the system. So in the bottom, we show the approach, like first, use the simple tool to find the tuning issues, and once you're confident that the system behaves as you like it to behave, then move on to a hardware switch benchmark. The first time we tried that, we got some pretty bad numbers. Why did we get the bad numbers? And then, I mean, from the reports of the switch test system, we just saw we had like packet drops, milliseconds of latencies, and said, why did we get good numbers with the L2 reflect, but so bad numbers with the switch test system? And luckily, we had this monitoring infrastructure set up, and there we also plot we can filter on the CPUs we are interested in. So CPU 1 and 2 are the real-time CPUs, or the ISO CPUs. Then we looked there at the interrupt queues, and so we have a lot of NetRx traffic on the real-time cores, which shouldn't be there. And here you see the packets that are inserted by the switch test system into the OVS, and then you see that these interrupts correlate pretty well with the amount of packets you insert there. What was the root cause of that? Well, we used the sflow, or we enabled sflow in the OVS. And we don't really need that, but for a test we enabled it. And the sflow samples some traffic and sends it out to a local connector via UDP. The collector runs on a non-isolated CPU. Then, by sampling too much, we overrun the collector, so the collector was not able to keep up with the packets we insert there, which shouldn't be a problem, because the collector runs on a non-isolated CPU. But unfortunately, we also didn't get the interrupt queues fully right, so it changed over, the affinities changed over time. And by that, the non-real-time CPUs were overloaded, and the interrupts somehow were also scheduled on these real-time CPUs. And after fixing that, the problem was gone, but the point I want to make here is to really monitor your system to find these issues. If you don't have the monitoring set up, it would be very, very hard to find it. And also with this minimalistic testing applications, like the L2 Reflect application, you will never find it because you don't put too much pressure on the Open vSwitch. So coming to the measurements, after we finally tune the system right and get rid of all these bugs. So one thing we had to do is to only use 2 of 4 ports per card. So we only used 4 ports in total because to get really good numbers, we had to do a one-to-one assignment of a PMD thread to a physical CPU. The system just had like 8 CPUs, and then you cannot, I mean, you need best effort CPUs, so you cannot just assign all these CPUs to the poll mode drivers. Then we also configured the Open vSwitch to bind the affinities, to use just one RxQ per PMD, also set the affinities of the RxQs so that they are not load balanced. We run the benchmark for 16 hours to get some realistic results, and we played around both with the frame size and the load of the system. And with load, I mean a load of 0 means we don't insert any packets. A load of 100% means if you just look at the time a packet is on the wire, then if the packets are back to back to back, like there's always a packet on the wire, there are no gaps in between, that would be 100%. So just this load does not depend to the system load, but just to the frames on wire. And this RFC 2544 benchmark uses 256 MAC addresses per port, which is quite a lot. I mean, it depends on where you come from. And then if you look at the frame sizes, so here on the y-axis you see the last in, first out latency in microseconds. Here on the x-axis you see the load. If you look at small frames, which are unfortunately the frames we have most in this industrial setting, like 64-byte frames, if there's not much load on the system, you have like 40 to 50 microseconds LIFO latency, which is pretty good, but the switch is only able to handle a load of like 70%. If you use higher loads, then you get packet drops and huge latencies, which is not what we want there. But if you increase the packet size, you see the numbers are getting better, because the effort in the OVS is not in copying data around, but really in handling reading the header of the Ethernet frame and finding the target port. So if you look here at, if you use 128-byte frames, we are able to get up to 90%. If we use larger frames, we are able to fully utilize the 1 gigabit ports. I think that's missing on the slide. So we have 1G ports. And with that knowledge, you can plan, like you now know how much load you can put on the system to get the numbers you're interested in. So let's conclude. Time is almost up. Maybe start with the problems we discovered. Firstly, the real-time tuning of Open vSwitch is not trivial, because first you have to tune the operating system, then you have to tune the Open vSwitch. There you have to do a lot of configuration to get a proper tuning for your use case. For high performance, you still have to spend many CPU cores. So you really have to throw hardware at it to get a decent performance. What we learned is that the Open vSwitch, out of the box more or less, is very well suited for low latency communication. Also, LIFO latencies below 80 microseconds can be achieved for reasonable loads relatively easily. But to get there, you really have to know your system, monitor your system for real-time issues, use a proper tuning, and you have to be able to work with kernel tracing to carve out all these tuning issues in the first place. The next steps for us are to analyze the effect of the OVS caches, like the megaflow cache or the exact match cache. Also do the same measurements with the XTP backend of OVS. Then maybe do some more dynamic tuning, like getting rid of this isol CPU kernel command line parameter, but use cgroup instead. Run the benchmark with VMs, but connecting VMs to a hardware switch system is somehow not so easily possible. And if I had to summarize the talk just in 2 bullet points, I would say Open vSwitch with the DPDK backend works very well as a real-time switch at the cost of spending many CPU cores, especially if you want to forward small frames. And still, you have to be realistic what numbers can be achieved there. So the LIFO latencies are still 5 to 10 times higher compared to a hardware switch like a scale-in switch from Siemens. And that's it. Thanks for listening, and I think we still have some time for questions.
Thank you both. Do we have any questions? Yeah, we do. Here, let's take a question from the audience.
Hello, thank you for the presentation. What is the gain, or what is the impact of setting, of having a real-time preempt kernel? Because you explained that you use idle CPU, IRQ affinities, etc. But I don't understand how a real-time kernel impacts the latency for if you already use idle CPU, for instance.
Yeah, let me. Am I audible? Not yet. Okay, here we go. Yeah, that's relatively, or it's not relatively simple, but it's you can answer it relatively simple. The preempt RT kernel gives you access to certain real-time scheduling algorithms and to priorities, which effectively allow you to be really the only one on that CPU and to be scheduled really fast. If you think about isol CPU, that there's nothing else running on the core, you're wrong. It's close to nothing else, but there's a lot of, there are several kernel housekeeping threads that are just required to keep your system operational, and you know, they won't be free of load. And some of the things that isol CPU, I'm not sure about the current state, that changes as preempt gets mainlined, but you know, isol CPUs might be doing something a bit more when you're doing certain things, and like no HC full, not available, or not fully implemented. So these kernel command line switches mean something a little different. And yeah, we are not assuming that, you know, that's basic setups. If you assume that you will have multiple applications, then you will need also those priorities. Maybe you want to share the core after all, because as we said, it's very expensive. And if you want to share the core after all, then you'll need those priorities and those scheduling algorithms.
Okay, thank you. Just one more question, if possible, a quick one. Did you benchmark the latency of Linux routing or Linux OVS without DPDK?
Yes, of course. So the first thing we did is to simply measure the system itself without any OVS, but just measuring with the cyclic test application, which is a pretty standard testing application to see if your system is well tuned. And there's no OVS involved, it's just measuring the interrupt latencies. And then we moved on to the OVS, and I mean, you cannot just measure the OVS. The OVS always runs on a system and runs on a hardware, so you always measure everything together. But that's why I said it's so important to start with minimal measurements like this L2 reflect to be able to drill down to the tuning issues you almost always have, and you first have to carve out.
Hi, thanks for your talk. I just have a question. For your measurements, were you just running in like a warmed up data path, or are you including any latencies, say, for first packets to be classified and stuff like that, and the software caches in OVS warmed up?
Yeah, so actually the RFC, so for the L2 reflect we have a warm-up phase anyways, and for the RFC 2544 measurement we also have a warm-up phase, but there the problem was that there's 1 second in between the warm-up phase and the actual measurement, and you have to configure the OVS so that the cache is not evicted in between, but we are not the first one who use the Spirent system to measure an OVS, and there are some things you have to configure in the OVS, like how long the cache is not evicted.
Okay, and just a related question, did you just use the default software caching in OVS, or did you disable all that for your measurements?
No, we use the default.
Okay, thanks.
Thanks.
Hello. Yeah, here. Did you test with other NICs besides the Intel i350? And
we mainly used Intel NICs, 350s, 210s even back at the time, or still 210s, and 550s, not more, and then vhost user, if you want to count that. And yeah, so they all show pretty similar numbers. Of course, the 10G card performs in this ping pong a little bit better. But surprisingly, in the beginning, it was not, because when we started the whole thing several years ago, the 550s had batching implemented, so they would not send a single packet. They would wait for 10 milliseconds or 1,000 micro or something. So you would, if you didn't send 32 packages at once, you would get like a 2 or 20 millisecond delay on the faster NIC, because they were batching. So that's the difference between, you know, what many of the guys talking here about high performance, that you always hear batching. Of course, you need that for high throughput. If you go for low latency, maybe that's bad.
okay, and about the 10 gig, did you see any difference between fiber and copper connections, or no?
Didn't try. Okay. I doubt it would be a difference, to be honest. And it's you know, it's a complex system you're measuring anyways. In effect, you're measuring 2 applications, 2 processors, 2 NICs, and the cable going back and forth. So you basically kind of have to double that. It's 2 times received, 2 times sent, 2 times going into CPUs. If you're unlucky, there might be some scheduling involved. So it's a super simple application, but it's still, you know, rough. We know, like, for example, this 31 microsecond example, you divide the number by 2, you say 15, it took 1 party, then you know cyclic test would be like at 5 to 7 on that core. So you could say, like, probably half of the time is spent for compute, which is basically just wake up and do something stupid and go back to sleep. And the other half is spent on the NIC.
Okay, thanks.
There's another question, I think.
Okay. Thanks for sharing. I have one question about this. I just wonder, in both sides, what's the burst size are you using this moment? Burst size for the NIC PMD.
Which assignment?
Burst size. You know how? So each time.
Burst assignment.
Yeah. Yes.
So for the 1G NICs, we use a burst of 1. But for this, I think it was the 10G NIC which did the batching, right?
Well, in the measurement application, we're using a burst size of 1, because we have 1 ball to play ping pong with.
Okay, that makes sense, yeah.
And obviously then once you put switches or network virtualization elements or something in between, but for the ping pong, it's a burst size of 1.
Okay. So for 10 gig, I will strongly recommend you contact Intel FAE about their NIC. Potentially, you have some, potential actually can tuning their receive buffer to allow you, send a single packets.
Okay, thanks.
Okay, thank you.
So, thanks for the presentation. Regarding L2 Reflex, do we, before running the test, do you run a kind of dry run by setting a loopback between on the test equipment, so that you can be sure that you are well tuned on the test equipment side?
Yeah, so if I got it right, the question has already been asked. We run a warm-up phase to be sure that we don't get first-time latencies there, and by that it should be, yeah.
So my understanding is that you have so L2 Reflex is a single application that runs on a different machine, and do you configure it so that you in loopback mode so that you can see the latency induced by the test equipment?
Okay, so this depends on which testing equipment we use. If we use the Spirent system, we cannot do that, but I mean, it's a hardware switch test system, so I don't see an issue. If we do it with the L2 Reflect and a second system, yes, we do these kind of loopback tests. And Henning showed the numbers, it's like 30 microseconds or so.
Okay. I mean, the approach there is really, if you start using new hardware, you would probably start with a cable loop, and even moving a workload into a machine would be considered using new hardware. So you would probably not introduce an OVS in the same step, but you would do PCI pass-through. And then, take it from there. Run the measurement for a long time and then see what a slight change makes a difference. Then you can say, okay, doing this makes it worse by 10 microseconds, like putting in 2 Cisco switches. I'm just guessing, or you can measure that, right? You take a cable, you put in a bunch of hardware switches, you can measure that.
Okay, makes sense, thank you.
But anyways, as you are interested in this, just have a look at the series, the patch to DPDK, which adds this application. Just start up 2 instances of that. They will find each other automatically by using broadcast, and measure by your own, and reply back to the mailing list.
Any additional questions at all for Henning and Felix?
Very quick.
We are already over time, I think.
I think you should say table tennis.
So when you transmit the packet, well, you receive the packet or transmit the packet. So when you only transmit the packet when you have a packet you receive to transmit. Mm-hmm. Do you measure the time it takes to complete the TX function? And do you measure the time it takes to complete the RX function with either returning 0 or 1 packet? Do you measure that so you can see also latency and jitter on that?
So in the past we measured that, but the problem is the influence of the measurement itself. So I mean, you cannot use clock get time for that, for instance, because there's a way too high overhead. You really would need to have a look at the TSC, and there it depends on which system you are running on, so it's really hard to get some realistic numbers there. That's why we dropped that again. And in the end, it doesn't count for us. I mean, for us, always the end-to-end latency is important.
Yes, but it will show the latency of the system itself as a help to monitor if the real-time parameters are really real-time. Yeah. If you call the RX function and you don't receive a packet, then the latency suddenly is high, then there's a problem. Yeah.
I mean, what will help there is maybe modifying even DPDK to leave additional trace markers, or finding some way of correlating your kernel trace with your DPDK trace, interleaving them, visualizing them, like kernel shark does. So I would, rather do something like this, because tracing is already ubiquitous. You have it in the kernel, you have it in DPDK. So use that and correlate the traces.
Okay, thanks.
Thank you both for a wonderful lecture. Appreciate it.